Okay. But I want to illustrate the organization for the Kramer rule. The Kramer rule say, look, you determine one determinant. I want to call, everyone call capital D. Capital D is one determinant is formed by coefficients in front of the variable. 1, 1, 1, negative 1. Do you understand where come from 1, 1, 1, and negative 1? Coefficients here is 1, 1, 1, and negative 1. Okay?
I don't see the whiteboard at all.
What do you say?
I don't see the whiteboard at all.
No. What's the problem today? Oh.
I don't see it either, Professor.
Okay, don't worry. Let me fix it.
When I minimize it, I do see it, and then it try to put it big, and then I see you again. Okay. So it's a glitch or something's going on. So I have to minimize, but I can only see it when it's very small, and I can't really see it.
Oh, yes. I don't know exactly what's going on. When I click in a screen share, okay. Now it's okay? No?
Now I see it.
Okay, yes? Good.
Yes, sir, I see it.
Okay, very well. Everyone saw or no?
Yes, sir.
Super. I don't know exactly what's going on. This is the technical issue, no? I don't know. Okay, let me keep going. This is example 1 to illustrate one thing. It's called Kramer Rule. Kramer Rule is the rule that we are using for solving system of equation, linear system of equation. It doesn't matter how many variables, how many equations. Different. Using determinant. So you define one capital D determinant that is formed by coefficients in front of the variable. Okay, 1, 1, look at 1, 1, 1, and negative 1. Do you see where I come from this number?
Yes, sir.
Okay, and don't forget how we compute that. We multiply this number and and positive, and you multiply this number and extra negative 1, no? Entonces es negative 1, and another negative 1, no? Because it's positive 1 and positive 1, it's positive 1, pero extra negative becomes negative, entonces the answer is negative 2, no? This is the answer of the capital D. Now we define another case dx. This is the most important moment, guys. It's another determinant in which you replace the column, the first column. By the way, the first column is the column of the x, no? And the column of the y is the second column. You replace the entire column 1 by the right-hand side number, que es a and 4, and the rest stay the same. I don't touch. I only touch the column of x because it's dx. And now compute this and this. Multiplication this and this is negative 8. And multiplication this and this. Remember que es negative when you go up, and negative is negative 4 and negative 2. Everyone follow me? I don't finish. I don't finish. I am in the middle of the process. Now I define dy. Okay, dy is exactly the same. A new determinant 2 by 2 because the system is 2 equations only, no? And 2 unknown. But you and the y, you replace that the column, the first column stays the same, 1, 1. But you replace the column 2, the column of the y, by the right hand side. Okay, and now multiplication. This is 4 positive. This is negative 8. Do you remember the rule to compute determinant 2 by 2? Okay, it was extremely easy. Using 2 diagonal. The diagonal is going down is positive. The diagonal is going up. We have extra negative. This is negative 4. Okay, finish. No, finish. No, not yet. Now the formula for the Kramer is x is equal dx divided by d. And y is dy divided by d. Who is dx? Minus 12. Divided by who? By d, negative 2. Negative divided by negative positive, 12 divided by 2 is 6. Exactly, we predict. And this is dy, get negative 4, divided by negative 2, of course, it's positive. And this is the solution. Exactly, we predict. Because the example is elementary, but I want to illustrate the new organization. It's the Kramer rule. So basically, Kramer discovered one rule, que is you computed the one general capital D determinant formed by the coefficients in front of the variable, okay, and you replace one by one. In this case, we have only two variables, x and y, but in the next example, we have x, y, and z, three variables. So you need to determine three, dx, dy, and dz. And well, finally, it's easy. You divide dx divided by d is x. Y is dy divided by d. And one problem in 3 dimensions is c is equal to dc divided by d. Okay, this problem not apply that idea, but because we have only x. Do you understand the idea of the Kramer rule?
Yes, sir.
Okay. Now let's open one more complicated example, 3 by 3, using Kramer rule. But in 3 by 3, remember my warning. In 3 by 3, always we are using software because it's too long. Maybe one student make a mistake, one stupid arithmetic operation, no? Except in the test, 2 by 2 by hand. 3 by 3 or higher software. And another specific questions que I mandatory enforce it to you doing by hand, you are doing by hand. Otherwise, no. Otherwise, we're using software. Okay, let me try to see example 2. A little bit more complicated, 3 by 3 system. Example 2. Is x plus y plus z, minus c equal 6. This is equation number 1. 3x minus 2y plus c equal negative 5. Equation 2. And x plus 3y minus 2c equal 14. Okay, this is our example, 3 equations, 3 unknown, x, y, and z. But I want to say, okay, maybe the question can fly in the air is, Professor, we study a lot of methods, okay, good. However, in the test, I specification. One question I specification. I need you solve this system using Kramer rule. Another example, no specification. Open. You using reduced echelon 4 or you using inverse matrix. Either way. Another question specification. I need inverse matrix. And another question gets open using either method. Kramer is, no, I don't know why some people lie. Personally, I don't lie. It's easy the organization, but it's too long the computation, no? And sometimes happen one thing I want to explain, but no. Okay, so what is the organization? You compute D. Okay, D is the determinant formed by 1, 1, minus 1. 3 minus 2, 1, 1, 3, negative 2. Okay, we can do by hand, but no, let's do it by the software. No? But let me finish the organization. The organization is dx. Remember, you replace the first column Here's the column of the x. This is the column of the x. This is the column of the y. This is the column for the z. By the right hand side number, so 6, -5, 14. And the rest stays the same. Likewise, dy is 131, but now we have 6, -5, 14. And C stays the same, no? -1, 1, and -2. Super. And DC is 131, 1, -2, 3, and 6, -5, 14. Everyone follow me in this organization?
Yes, sir.
Eso. Okay. Let's move on. The Geogebra Classic. Okay, Geogebra Classic. I open one new, totally in blank, no numbers. Geogebra Classic. Switching to the screen. Geogebra Classic. Boom. 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 Do you see Geogebra Classic?
Yes, sir.
Also, you will start at the beginning. Let's format the matrix. The matrix D is 1, 1, -1, 3,
-2, 1.
-2. Help me. No, I prefer. Okay, you checking my word. See, I make a mistake. Okay, you correct me. No, don't worry. I appreciate so much your help.
No problem.
Okay, this is D, the matrix of this. For a moment, stay like that. Let me see if it's possible. Copy and paste. Right click, copy. Oh no. Okay. Copy. Paste. Control B. There you go. Let me try to do several times. Control B. Control B. This is D, dx, dy, dc. Okay. So you replace and the first one, the first column by 6, and -5, and 14. Okay. Okay. Now to save time, I copy down, copy, and paste here. Control B. Boom. Control B. Boom. I have my 4 made. Okay, I form it one by one. I select the first, right click, create matrix. I want to rename because the name of this and my problem is capital D. Rename. Capital D. Okay. Now in the CAS, I put determiner. Determiner is D-E-T. No capital. D-E-T-E-T. Determiner. Look at that. Determiner matrix. Determiner matrix. What matrix? D. Capital D. Press enter. Bam. -3 is the determinant of this matrix. Okay. -3. I select again. Create a matrix. Select everything. Right click, create a matrix. The name of this guy, rename is DX. Like that, DX. So capital D and no capital X. Either way, you can call Maria if you want. Again, determiner. Okay, determiner DX. DX. Press enter. -3. What do you think is a value for the for the x. According to the Kramer rule, is divide dx divided by capital D. Negative 3 divided by negative 3 is positive 1. Let's do another. dy. Clip. Create matrix. The name of this matrix, you press right click on the name of the matrix and you put select rename. dy. Capital D, no capital Y. Boom. And determine again. Determine capital Y. dy. Press enter. Es negative 9. Wow. Es negative 9. Entonces negative 9 divided by negative 3 is positive 3. It's the Y value. And finally, create the matrix for dz. Create matrix. Okay. Rename. The name of this is dz. dz is the new name. And we compute the determinant. Determinant of the matrix dz. dz is positive 6. The positive 6 divided by negative 3 and negative 2. Okay? So I compute that. Super easy. I come back to the whiteboard to see the final answer. Okay. 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 Whiteboard now. Yes or no?
Yes, sir.
Okay. The answer of this guy was negative 3. The answer for this guy was negative 3. It's a coincidence. The answer for this guy was positive 3, no? Positive 3, no?
No, negative 9.
Negative 9. Sorry. Let me see my paper. Yes, you're right. And this C, the answer was 6 positive, no? Now ready to apply Kramer rule. Kramer rule say x value is the division dx divided by dx divided by d. In our example, dx is negative 3 divided by negative 3 is positive. X is what? Y is equal dy divided by d. And negative 9 divided by negative 3 is positive 3. Y value is positive. And finally, z is dc divided by d. dc is positive 6, d is negative 3. The answer is negative 2. Therefore, the solution for this system is the triplet order 1, 3, negative 2. X, Y, and Z. Any question? Kramer rule. I have a question. In this moment, you see the 3 different approaches to solving linear system of equations using matrix. The first one we studied, remember, was reduce the echelon. And you get the matrix A and put together for the matrix B. And you apply RREF. This is the first approach. The second approach is you take the matrix A, by the way, it's the same of this. You find the inverse a multiplication matrix by B. No, this period is not regular multiplication. It's a special multiplication of the matrix, and you get the capital X vector. It's a vector XYZ, no? YZ. This is number 1, this is number 2. And what is number 3? Number 3 is Kramer rule. Kramer rule. What is the formula for the Kramer rule? This formula. Entonces, what do you like? Number 1, number 2, or number 3? I want to hear opinion. Your opinion. Suppose you are engineer or scientist, and you need to compute a system 25 equation and 25 or no, and you can use, of course, software. What method you apply? What method? Number 1, number 2, number 3. I don't hear. Activate the microphone. Number 3. Number 3. Number 3. Giovanni say number 3. Christian, say number 3 again. The other students have no opinion. For example, they will not have your opinion. Joyce, you say something.
I said number 3.
Number 3 again. Wow. Yeah. Agree. Everyone is agree. Wow. Okay. I like Kramer. Okay. Disadvantage of Kramer. Disadvantage. Suppose you. Okay, I know a lot of people, smart people, professional people, like Kramer Rule. Okay, engineer, I know. However, what are the disadvantage? Suppose when you compute D, the answer is 0. Ooh, what the hell? And when you try to apply Kramer Rule and you cannot divide it by 0. So what means this idea? And suppose also dx, dy, and dc is not 0. Suppose hypothetically. 1, 2, 3. Interpretation this. Suppose another case in which d is 0 and dx, dy, and d is 0. Entonces, in this case, in both cases, when the d is 0, here and here, look, is not applicable Kramer Rule. It's impossible to apply. What is the reason? What is the reason behind this idea? Maybe it's a special case in which you have no solution or infinity many solutions. Okay? But in this case, when the D is a number not 0, it's because we have no solution. And when the D is 0, entonces it's like a 0 over 0, no? So this is 1 over 0. It's obvious, it's undefined. It's undefined. Entonces, si es undefined, no solution. However, when it's 0 over 0, 0 over 0 maybe is not undefined. 0 over 0 is undetermined. Undetermined. What means undetermined? Okay, undefined is a word que mathematicians create to express it. It's impossible to find the solution. Impossible. This is synonym to say impossible. Undetermined is unpredictable. Maybe is any number, right? Because suppose this statement, no? This statement, no? 0 divided by 0 is 5. You cross multiplication. And 0 times 1 is 0, and 0 times 5 is 0. This is a true statement. So any number here, undetermined. This is the reason satisfy this statement. Therefore, in this case, when you have infinitely many solutions. Infinitely many solutions. But you have no information clear about the amount of the free variable. That's the only disadvantage. But why don't you say, oh, I don't care, free variable? Okay, I understand. So you don't care, maybe Kramer Rule is good. Okay? The Kramer Rule is not applicable when the capital D is 0. When the capital D is one number, yes, that's perfect. Okay, however, if you want to know what is my favorite is echelon. In my opinion. I respect opinion. Okay, you have your opinion. I respect opinion. Okay. Entonces now, so you have no question, everything is clear or no? Clear or no? Confusing? Clear. Very well. Let me study now. Switch again to the whiteboard. Okay. Let me switch into erase the board, everything clear. Okay, I want to study, guys, some property. This is extremely important, and it's a little bit confusing, and it's a typical question on the test. Let's do one cup property of determinant. Okay, let me try to discussing some property. Actually, we have a lot of property. However, I condense in the lecture today only five property. What is the number 5 property? The number 5 property say the value of a determinant change sign if you two row or column, maybe column, or column are interchangeable. Interchange. Okay, let me explain using one example. Okay, suppose this elementary determinant 2 by 2. Okay, this is applied for any dimension, 25 by 25, whatever. But of course, it's easy to do by hand, 2 by 2, no? Suppose this determinant. By the way, this is, remember, the computation is easy. The multiplication, this and this, plus, and this and this, minus, no? Entonces, 2 times 5 is 10. Minus, because 4 times 3 is 12, but we have minus 1, entonces minus 12 is negative. Suppose now I interchange two rows. Suppose the row, this is the row 1, this is the row 2, and you interchange. You put 4, 5 here, and 2, 3 here. Okay, do you see the action? Okay, I did that. Interchange two rows. After I promise I want to interchange two columns. And now, surprise, I compute the determinant again. Plus, minus. Now it's 12 minus 10. It's positive. Do you see? Look at the relationship. Okay. When you interchange two rows, doesn't matter if it's the 1 and 2, suppose one super big determinant, que es 25 by 25. It's a huge matrix, huge determinant. And you interchange the row 1 and the row 24. So you replace the row 1 by the column 24. And the column 24 I replace in the column 1. Without do anything, I know. This is the original determinant. The answer is negative 2. The new one after the transformation is positive 2 because change the sign. Let me see now what happened with the column when the column change. Okay, now my issue now is I put this is the column 1 and the original. This is the column 2. I interchange column 1 and column 2. Now we have a new one get 3, 5, 2, 4, right? Do you understand the thing I am doing? Now multiplication. 12 and 10. 12 and 10 is positive 2, exactly the same of this. It's opposite sign to the original. Do you understand the property number 1? And this is valid regardless the dimension for the determinant. Super big determinant, when you interchange two rows or two columns, so you interchange 3, so you, for example, you interchange 1 and 2, and you interchange 2 and 3, you are doing two changing. Therefore, it's negative 1 and negative 1, double minus, stay the same. Because you change twice, or even number of the change, the same value. Si es even, y si es odd, you intercept 1 time, 3 times, 5 times, entonces the sign is obvious que change. Any question about the property number 1, guys? It's
No,
theoretical.
no.
This is theoretical. Now I promise I bring an example. In the review packet, we have examples. In the review packet, yeah, in the review packet. Okay. So now let me write the property number 2 now. Property number 2 is easy to understand. This is property number 2 is easy to understand. Property number 2, look, is if all the entries, these name entries, is synonymous, guy, to the element inside. The number. This is synonymous to say number. In the book, using the word entry. In any row or column. Okay, look, this is the most important thing. In rows plural, column plural. And when we study the matrix, we are talking about only row operation. Never row, never column. And determinant, no, both. Equal to 0, equal to 0. Then the determinant is also 0, equal to 0. This is obvious. This is elementary idea. But just in case, I want to put one couple of examples. Suppose 0, 2, 0, 3. I put the column number 1, just 0, 0, 0, 0. When you are doing the multiplication, 0 times 3 is 0. 0 times 2 is 0. So 0 minus 0 is 0. But another more complicated, for example, this 1, 2, 3, 0, 0, 0, 4, 5, 6. When you see that, without do anything, you see, wow, the entire row 2 is just 0, 0, 0, 0. The answer is 0 according to the property number 2. Because when 1, every element, all the element of the one row or the one column, suppose another example. Here is similar. But we have 1, 2, 3 here. 4, 5, 6. 0, 0, 0. Regarding the position, it's also 0. Because the reason is because in this case we have one entire row 0, and we have one entire column 0. Makes sense, right? Because assume that you expand the determinant using the row 1. Entonces 0 times cofactor plus 0 times cofactor plus 0 times cofactor es obvio que sí. Here 0 times cofactor plus 0 times cofactor plus 0 times cofactor. But this is elementary. This is using the common sense. But just in case I want to refresh your memory, no? Property number 2. Property number 3 is a little bit more complicated. Is number 3. If any 2 row or column of a determinant have same entry. Remember, entry is a word that we use in the book to indicate value of the element. The value of the determinant is again 0. One example elementary, another example non elementary. Both these. 2, 3. 2, 3. It's the same rule. Well, when you compute this and this, plus 2 times 3 is 6, and this is minus 6. The answer is 0. This case is straightforward, but not always is straightforward. Look this example. Suppose this example. 2, 5, 2, 2, 5. Uh-huh. 3, 6, 3, 3, 6. And 2, 2, 5. By detecting the row 1 and the row 3 is the same. 0 have the same entry. But we have more than this. Look, not necessarily it's the same. Maybe it's proportional. Proportional is, okay, when you multiply, for example, look, and not necessarily is exactly the same. Maybe proportional. Suppose one example get like that. Look, 2, 2, 5. 3, 3, 6. 4, 4, 10. I can discover, wow, the row 1 and the row 3 is not the same, but they are proportionally because you multiply element by element. The row 1 by 2, we get exactly the rank row 3. Okay, entonces 2 times 2, 4. 2 times 2, 4. 5 times 2, 10. Okay, again is 0. Okay, entonces this property is not necessarily equal. It's equal, of course, much better, no? But si es proportional, es obvio que es 0 the determinant. Okay, well, suppose you say, well, one professor, you explain, I understand, but how you prove that? How you prove that? Okay, the proof of this, look, the proof of this is elementary. Look, in the property number 1, we study, let me recall, in the property number 1, we study that when you interchange two row or two column, the value of the determinant is the same value but opposite sign. Entonces, bueno, okay. Let me try to understand this using this idea. Suppose que it's exactly the same. This example, 2, 2, 5, row 1. And row 3 is exactly the same, 2, 2, 5. See, if you apply the property number 1, you interchange this and this. I suppose que let me try to prove using the contradiction. Suppose que it's not 0. Suppose que it's another number, 10. And when you interchange row 1 and row 3, the answer should be negative 10. According to the property number 1, is always valid. So what is the only number? What is the only number that when you change the sign, it stays the same? 0, because 0 have no sign. 0 is happy guy. When you interchange is 0 and 0. I prove by contradiction that when you have, of course, we can do by the long way. You expand this determinant using cofactor. Remember the formula in the last class is too long. And you discover que es 0, but it's too long and you spend time. So the property help us to do the problem a little bit fast. Okay, property number 3. Let me study now property number 4, it's very, very important. Any question, guys? Any question? Everyone follow me? Confusing, clear? Confusing, clear. Okay, good. Okay, good. Property number, what number? 4, no? 4? 4. You are right, 4. Okay, I want to erase the board because too much information. When you write too much information on the whiteboard, the whiteboard becomes a little bit slow. Okay. Number 4 property say. Number 4 property say. Number 4 property say. Wow, what the hell? If any rows or column of determinant is multiplied by a number. Of course, non-zero. Zero is bad guy. Another arbitrary number, k. The value of determinant is also changed by the same factor. I want to call, well, either way, the same factor. Let me try to understand with the example, because blah 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 too much work and don't, it's not clear there. Let me try one elementary example 2 by 2 que it's easy. And this is valid for any dimension, guys. Both the determinant. When you compute this determinant, the answer is 10 positive and 12 negative, you know? Entonces es 10 minus 12. 10 minus 12 equal negative. Now suppose now that I multiply the first row, is this, row 1, by one factor. So I multiply the factor, let's do it in several examples. Factor 2. So multiply by 2. So we get a new determinant, que is 4, because 2 times 2 is 4, no? And 2 times 3 is 6, and the rest, no, stay the same. So the operation we are doing was only multiplication, the row 1 by the factor 2. I select arbitrary, no? In other example, I select factor 3, factor 5. And let's see what happened with the value. The value is 20 and 24, pero negative. It's negative 4. Ooh, okay, what is the issue? The issue is, this is the original value. It's negative 2. When you multiply only one row, okay, I select the row 1, but I can't select row 2. Or I can select column 1 or column 2. Only one. So you multiply 2, entonces multiply by 2 and by 2 again. Pero si you multiply only one row or only one column by the factor 2, the new value of the determinant, new value is also multiplied by the same factor. Okay. A little bit confused. At least for me, it's a little bit confused. Let me try another example. Suppose I want to multiply the column 1. This column. The column 1. So the column 1 I want to multiply by a factor 3. Okay. So is the new determinant after the transformation is 3 times 2 is 6. 3 times 3 is 9. No, sorry. Column 1. So it's 12 here. And the rest stay the same. Okay? 3 and 5 stay the same. So the thing I did was, I multiply the column 1, que es this, by factor 3. I don't know, hypothetical. I assume a factor 3. In another example, you see a factor 20. And let's see what happens. When you multiply this at 30, and when you multiply here at 36, minus. Minus 6. Where I come from, this minus 6 was the factor 3 multiplied by negative 2, give me negative 6. Conclusion. if you multiply one determinant, I don't care, get 2 by 2, 3 by 3, 80 by 80, any dimension, multiply one row, arbitrary, 1, 2, 3, 4, 5, by one factor, the entire determinant by the same factor. This is confusing, at least for me, because in one moment I explained to you, for example, you have a matrix, it's different to determinant. It's important to warning you in this idea. Suppose I multiply by 2. This matrix multiplied by 2. This is the okay. This matrix I call capital A. This is 2A, no? And 2A is equal 4, 6, 8, 10. Then you multiply any entry by the factor. But it's a multiplication of matrix. Time is the property we study now is different. It's determinant. It's another completely different word. It's another mathematical object. So you multiply only one row, only one column arbitrary, and the value of the determinant is multiplied by the factor. Suppose you multiply all the rows by the factor. In this case, get 2. You introduce artificially 1, 2 in the first row and another 2 in the second. Entonces 2 and 2 together is 4. Multiplication by 4. Clear? It's important, guys, to understand the difference between matrices and determinant. It's completely different concept. Okay. Property number 5. Property number 5 say, if you, this is important, extremely important. In my opinion, this is the most important. If you apply row operations, I suppose that you remember row operations. Now, when you study echelon, we study row operations. Just in case, don't worry. I know because this is a little bit confusing. In the review package, we are doing several examples of the row operation. But in this case, row operation or column operation, Remember, in the determinant, there are no differences between row and column. In matrix, no. In matrix always is row only. Operation. The value of the determinant remain unchangeable. Wow, it's an elegant way to say it doesn't change. It's unbelievable. Some people don't understand very well this property because try to use your common sense. This is totally opposite to the common sense. Let me prove. Suppose one elementary example. Suppose this determinant 2, 3, 4, 5. Okay, I did before, no? The answer is 10 minus 12 is negative. And suppose I'm doing this row operation. Suppose 2 row 1 plus row 2 storage in row 2. Let me try to refresh your memory about the idea behind this row operation. That you obtain a new matrix or determinant, in this case, no? In which the row 1 stay the same, but participate in the game, no? Because it will multiply by 2, adding with the row 2 and the new number storage in the row 2. So basically is 2 times 2 is 4, if 4 plus 4 is 8. And 2 times 3 is 6, and 6 plus 5 is 11. Do you understand where I come from? 8 and 11? No? No clear? Okay. Repetition. 2 times 2. Because the row 1. row 2, plus, row 2, the corresponding in the same column, no? Is 4 storage in row 2. 2 times 2 is 4, if 4 plus 4 is 8. This is come from this 8. The second is two, as a factor, arbitrary factor, and the row operation. Remember, the typical format for the row operation is if we have a factor, we have a row that contains a pivot. In this case, no pivot, but it's okay. Plus another row, a storage in the new row. So this is the new row, and this is the old row 2. So 2 times 3, no? Because we are doing row 1. Row 1 is 2, 3, plus 5. They belong to the row 2 in the same column, no? Is equal 6 plus 5, 11. Okay, let's see what happened. Surprise! Let's see what happened. When you multiply 2 times 11 is 22. 8 times 3 is negative 24. The answer is negative 2. Wow, amazing. It's the same value. Unbelievable, but it's true. Okay, this is one elementary example I try to illustrate, but this is the rule. This is a property. Suppose you have one big determinant, 25 by 25, 50 by 50, and you apply row operation. Well, you are doing nothing. The value of the determinant is the same. And column operation. Let me try to illustrate column operation also. Okay, suppose I propose the following column operation. Look, 3 times, que es a factor, arbitrary. Column 1 plus column 2, storage in column 2. Okay, the new determinant formed by this is, okay, the column 1 stay the same. The only column that change is the column 2. Entonces, 3 times column 1, que the first element is 2, plus, let me see, 3 times column 1 plus column 2, que es, column 2 es 3, ¿no? Es 3. Es 3, yeah. Entonces, 3 times 2 is 6, plus 3 is 9. Okay, 9 here. And the column 2. This is column 1, guys. This is column 2, no? We are doing this operation in between column 1 and column 2. Now, 3 times is a factor. It's a factor, okay? It's like crazy, arbitrary. Supposing in the test I put 4, 5. You multiply by 5. Each element in the column 1, 3 times 2 plus 3 is 9. Likewise, 3 times 4 plus 5, no? This is 12, 17, no? It's 17. It's 17. Okay, let's do the multiplication. The multiplication is 2 times 17 is 34. 9 times 4 minus is negative 36. Again, is negative. This is really unbelievable. So when you perform row operations or column operation on the determinant, the value stays the same. Dun, dun, dun. Do you see or no? Of course, you need practice. But in the review packet, we are doing practice, doing problem with the row operation and column operation. No? Okay, we have one more property. Yes, we have one more property. The last one is easy to understand. And after, let's see example to illustrate the application of this new idea. Okay, the property number is 6, say. Diagonal is the property about property number 6. It's about diagonal. diagonal determinant property. What is that? When we have special matrix, it's called diagonal. For example, 2, 2, 3, 0, 0. What is the reason it's diagonal? It's diagonal because, for example, you have this 2, 3, 4, and the rest is 0. This is a diagonal matrix because we have only number in the main diagonal. The rest is 0. So to compute it by hand, it's super easy because 2 times 3 is 6, and 0 times 0 is 0. So the answer is 6 possible. Here's the multiplication. And you apply the same idea in any matrix, regardless the dimension. Suppose case 100 by 100. The answer is 2 times 3 is 6 times 4 is 24. Okay? And this is also applied. A little bit complicated to prove that. If, for example, we have diagonal, and below the diagonal we have 0, but above the diagonal, no, we have just a number. This is called like a under diagonal. The answer is also 24. I don't care. This number do not participate in the game. You multiply this number. Likewise, you have, for example, 2, 3, 4. You have 0 above. And we have arbitrary number below. It's the same. And this is upper diagonal matrix. Upper diagonal, in this case, no matrix, it's determined. Please.
Is it safe to take 0 when you see something like that?
I don't understand. Come on, speak loudly and clear.
Okay, do you hear me now?
Yeah, perfect.
Okay. It's just best, instead of, you could just make them zeros. Always look at them as zeros, correct?
Diagonal matrix is a special matrix que have just 0 and we have only number in the main diagonal. So it's super easy to compute the determinant because the only thing you should do is multiplication, the number in the diagonal. This is the property of the diagonal matrix. But it's also applying another particular example in which you have below 0 or above 0. As you have both, it's better, no? This is a perfect diagonal. And this is not perfect diagonal. It's half diagonal, under diagonal, and upper diagonal. But the rule is the same. The rule is the same. The property is the same. It's clear or not clear, Giovanni? Good. Okay. Okay, let's move on. Not clear? Joyce?
Yes, sir. Thank you. Yes, I got it.
Okay, you got it. Okay, let me see if you understand or you don't understand. Now, I need to using imagination and common sense to solve that problem. This problem, unfortunately, we can know example now, but this example is to compute that using the property. And impossible doing by software because sometimes in the problem we have a letter 1, 2, 3, UBW, what the hell, XYZ. This is a given. For example, this determines somebody compute that and the answer is -4. Yeah, I want to compute. Compute. It's a given. I want to compute the following determinant, no? It is XYZ UBW 1, 2, 3. Question mark. I have no idea what is the value of this. And we're using the property we studied before. What property you study? What property we using in this example? Number 1, number 2, number 3, number 4, or number 5?
Number 1.
Number 1, because you can see the differences between this determinant and this determinant is only if somebody interchange row 1 and row 2. I don't know if you interchange in the original or you interchange in this. And the row number 1, this gets the same value, but the opposite sign. Therefore, I know using the property number 1, que the answer is, negative, positive
4. Positive.
Positive 4. Because it's the same determinant, but somebody know me interchange two rows. So the same value. Another way to solve the problem is look. I realize there are two rows interchange. So I want to put in the same original place. Okay, similar to the original. I put 1, 2, 3. UBW stay the same. Nobody touch UBW. Row 2 no. But XYZ yes. I know using the property number 1, when you are doing this operation, you are fed by negative 1. And I know that the value of this determinant is negative 4. Therefore, we have minus 4. The answer is positive. Any question? Any question?
No, sir.
Okay. Let's do another. Go ahead.
No question. You said the first equation you said negative 4 was given. I was wondering why you had negative 4 and positive 4.
It's giving. Giovanni, this is given. Suppose I put no negative 4. I put 400. This is 400. So what is the answer of this? The answer is negative 400. Because we have two rows as interchange. Okay?
Yes, sir.
Let's move on to example 2, que is similar, very similar. Again, it's given this idea, que es negative 4, no 400. Forget about 400 for a moment. And you need to compute this one, que es X, Y, Z, UBW, and 2, 4, 6. Wow. What is that? How many transformations we are doing here? What property are you using? Number 1, number 2, number 3, number 4 property. I have no idea. So what are the differences between the original and the new one? Just give me. Well, I can see that you interchange row 1 and row 3 again, no? Oh, no. Row 3 is 2, 4, 6, no 1, 2, 3. There's somebody multiplication by 2, no? I know using the property, what number? I don't remember the property number 4, no? When you multiply one column or one row by one factor, the value of the determinant is also affected by the same factor, no? Okay, let's do it step by step. Okay, step by step is, look, I realize that 2, 4, and 6 are very similar to 1, 2, 3. Yeah, I factor out 2. So I apply the property in your direct senses, inverse it. I factor out, no multiplication, factor out. Entonces, X, Y, Z, UBW, 1, 2, 3. Everyone understand very well this idea or no? Because the great common factor between 2, 4, and 6 is 2. I factor out these 2. Because the property say that when you multiply one row or one column by one factor, the entire determinant is multiplied by the same factor. So we can do in different directions. your multiplication or your factorization. Now the rest was similar to the previous example. I interchange two rows, so I put the -2 because I know the property number 1 that when you interchange two rows, the value of the determinant is affected by change the sign, no? Is the sign is changing. Now, this is look like exactly the same of the original, I guess -4. This information is given. I multiply positive. Any question? Any question? Any question? Any question? Do you see or no? Confusing. Okay, in the first example, we are doing only elementary interchange to row. The answer change the sign, -4, +4. In this case, we are doing two properties. You interchange two columns, two rows, sorry, and also factor out. The common factor, the great common factor, that was 2. And after become like a -2 when you interchange two rows. And -2 and -4 get the original value of the given answer is positive. Super? Question? Question? Wow. But I want to complicate a little bit your life now. Example 3. Example 3, look. Suppose this, 1, 2, 3 again. I like 1, 2, 3. But we have x minus 3, y minus 6, c minus 9. Wow, this is a row 2. And 2u, 2b, and 2w. And it's the same problem in which it's giving the original determinant, this one. 1, 2, 3, UVW, right? Now I need to compute this new one. If somebody affect different a little bit, no? But I can see que 2 is a great common factor. Yes or no? I factor out. That 2, 2. 1, 2, 3. X minus 3. Y minus 6. It's a variable. C minus 9. UBW. Okay, nice. Okay, entonces I would like, I will be happy if I can destroy this -3, -6, and -9. I don't understand very well what the hell is that. However, I can see 3, 6, and 9 are multiple of this. Like 1 times 3 is 3, 2 times 3 is 6, and 3 times 3 is 9. Entonces I propose you doing row operation. In this case, row operation. That's 3 times row 1. This is row 1. No? This is a row. Plus row 2. Storage and row 2. Okay. Don't forget that to copy again. Entonces, I am doing row operation between row 1 is this, and row 2 is this. Okay? I know it's hard for the students see the row operation, but you need to tell your brain to see the row operation. So look, it's 3 times row 1, element by element. The element in the row 1 is 1, 2, 3, no? So it's 3 times 1 is 3. Plus this, it's obvious that this 3 is cancelled with this 3. So 1, 2, 3 stay the same. UBW stay the same, because basically we are working only using row 1 and row 2. Entonces this is x, and 3 times 2 is 6, positive, minus 6 negative y. Wow. And 3 times 3 is 9, positive, minus 9 is cancelled. Also, I stay alive, only the variable z. And that's it. No, because the order, remember, the original was look, and the original was, these two stay, and the original was 1, 2, 3 is okay, but UBW here, no? UBW here, let me see, yeah, XYZ here, right? This is the original. Okay, I know that the value for this determinant is -4, no? But when you interchange two rows, I know that it's affected by extra -1. This is -4 and -2 together is positive. Again, the answer is positive. Do you understand the idea? So little by little, you are doing transformation of the given determinant in order to look like similar to the given information. Okay, so you have this, okay, the answer that you want to compute. I have no idea, totally lost. However, I know this fact, 1, 2, 3, UBW, XYZ, is equal to -4. I transform a little bit, one by one. The first thing I did was remove these two. I factor out outside, like a 2. And after, I need to use my common sense and imagination and remove these 3, this 6, and this 9. How? We are doing row operation between row 1 and row 2. And finally, interchange row 2, interchange row 3, no? Here, switching that, interchange. Now, remember when you interchange, you have to put the opposite sign, -1, to say -4 and -2 together, and it's positive. Okay, guys? Now, those we have no time to start review. We have review to say next, no, this Thursday. We start review, okay? We Spain according to the syllabus, we Spain November 12 and November 17. I suppose that we have time, no? If we have no time, no problema, because we have November 19, and November 19, I send to you the test, depending, okay? Okay, super. Okay, super, Felix. Okay, see you guys. Bye.
Thank you, sir. See you on Tuesday.
Bye, Professor. Thank you.
Sure.
Thank you, Professor, again. Have a great day, sir.
You too.